Let's continue with the discussion on the Eyring equation. Now we turn our attention back to the activated complex. We make a crucial distinction regarding its degree of freedom. We assume that one specific molecular vibration of the activated complex is the motion that caused the breakdown of this activated complex into the product. So it tips it through the transition state. While this important motion is typically a one-bond vibration, especially the asymmetric stretching motion, which move the atoms along the reaction coordinate to yield the product. So we must treat the partition function for this one specific reaction coordinate vibration, which is the asymmetric vibrations, separately. So it will retain the standard form of the vibration partition function. And this is the partition function specifically for the asymmetrical stretching. The symbol nu here is the vibrational partition function equations, which it represents the frequency of the specific asymmetric stretching vibration. Because these oscillations correspond to the complex actively falling apart, it is essentially a breaking bond, so the restoring force constant is very low. As a result, the frequency nu is much lower than the frequency of an ordinary stable molecular vibration. Since the value of this nu is very small, then the term here will become a value which is very much less than 1. So this small argument will allow us to use a power series expansion such as a Taylor expansion for the exponential term in the equation. We can expand the exponential term from these equations using the approximation. So the partition functions for the asymmetric stretching mode can be simplified into this expression. Now we can define the total partition function for the activated complex, okay, by factoring out this special reaction coordinate partition function for the asymmetrical stretching from the remaining degrees of freedom, which is denoted as Q with this double decker. So the term Q double decker account for the remaining degree of freedom in the transition state. This is the 3 translational, the rotational, and the remaining non-reaction coordinate vibrational mode. Now we are ready to derive the final form of the Eyring equation. Recall that the relationship from the equations of K2 equals to this kappa multiply the frequency of the vibration multiply the equilibrium constant for the activated complex. So for the bimolecular reactions where involve the reactant A and reactant B to form the activated complex, we derive the equilibrium constant from the partition coefficient. So we can relate this with the rate constant for the whole reactions from A plus B to give us the product. So the rate constant for the whole reaction K2 equals to K mu frequency, which is this part, multiply the equilibrium constant for the activated complex, which is this piece here. So we substitute it into the equations in this green box, and then from this equilibrium constant for the activated complex, it has the partition coefficients, for the activated complex, which it can be substituted by the expressions that we have seen just now. Okay, when we replace these expressions into the equations, then it will be able to let us cancel off the frequency of the asymmetrical vibrations. So both of these can be cancelled off and retain only these expressions. Okay, so now we have the equations to determine the rate constant for the whole reactions. Okay, so it relates the macroscopic rate constant to the molecular parameters of the reactants and the transition states, which it allows us to account for the molecular structure and complexity in the reaction kinetics. And this is how Eyring equations, okay, relates the reactions rate constant with the partition coefficients. Let's use these reactions to practice assigning degrees of freedom to the reactants and the transition state. These reactions involve hydrogen atom with the bromine molecule to form the activated complex, proceeding through the complex and then give us the product. So we have to determine the degree of freedom for the reactant, which is hydrogen atom and also the bromine molecule. For hydrogen atoms, the total degree of freedom is equals to 3 because it has only one atom, so 3 multiplied 1 equals to 3. All three are translational. The partition function contributions is given as the symbol of Q subscript T superscript 3. For bromine molecule, there are 2 atoms, so the total degree of freedom equals to 6. 3 of them will be the translational, 2 of them will be the rotational, and 1 of them will be the vibrational. So the partition function contributions is given by these representations. For the product of these reactions here, which is the formations of the activated complex, the bromine molecule can be temporarily bonded to the hydrogen atom, okay, in the formations of this activated complex. So assume that this is a non-linear molecule, and this molecule consists of 3 atoms. So the total degree of freedom is equals to 9. 3 of them will be the translational, 3 of them will be the rotational, and the leftover 3 will be the vibrational motions. So this will give us the degree of freedom, which is Q subscript T 3, Q subscript R 3, whereas for the vibrations, we need to exclude the asymmetrical vibrations, okay, because we have already taken into the account when we applied the equations that we derived just now. So it left only 2 vibrations, okay, because we remove one of the vibrational mode, which is the asymmetrical stretching. We can now write the full Eyring equation for the bimolecular rate constant K2 in terms of the specific partition functions calculated in the previous slide, using the superscript to clearly show the degrees of freedom involved. By carefully inspecting the ratio, we can see how the structure of the transition state relative to the reactant. For instance, moving from two separate species. In this example here, we have hydrogen atom and bromine molecule to a single non-linear activated complex results in the loss of translational degree of freedom, but a gain of rotational degree of freedom and vibrational degree of freedom. Here is another example involve the unimolecular reaction for the decomposition of diazomethane. The task is to determine the degree of freedom for the reactant and the transition state, which is for the activated complex form, and then write out and simplify the expression for the unimolecular rate constant K1. For unimolecular reaction, the transition state theory rate constant K1 will involve the ratio of the transition state partition function, okay, to only one reactant partition function. So we have seen these equations in the previous slide, and now we have to evaluate what are these partition functions for the activated complex and also the reactant. We perform the degree of freedom calculation for the reactant. Okay, so there are 5 atoms in this molecule. So n will equals to 5. Therefore, the total degree of freedom for this molecule is 15. Okay, so upon this 15 degree of freedom, 3 will be the translational, 3 will be the rotational. For vibrational, it is equals to 15 minus 3 minus 3. The balance is 9. Okay, so for the reactant, the partition function is given by these expressions Qt3, Qr3, and Qv9 for each of the motion. Whereas for the activated complex, there are 5 atoms, okay, in this activated complex. Therefore, there are also 15 degree of freedom. Translation or rotations, okay, each of them will have the 3 degree of freedom. For vibrational, since one vibrational is dedicated to lead the product formations, the remaining degree of freedom include only 8 vibrational mode. Therefore, we have the partition function for vibrational mode is equals to 8. Now we substitute this into the rate constant expression. For the activated complex and also for the reactant. The translational and rotational partition function will cancel off since they are the same for the reactant and also the transition state. And this simplifies the expression, leaving the vibrational component. Okay. The Eyring equation can also be expressed entirely in terms of thermodynamics, which is extremely useful for relating the microscopic theories to the macroscopic data. The objective is to express the equilibrium constant for the activated complex in terms of Gibbs free energy of the activations, which is represented with the delta G double decker. So delta G double decker is defined as the difference between the standard state Gibbs free energy of the transition state and the standard state Gibbs free energy of the reactants. All right. So by definitions, the relationship between the standard Gibbs free energy change and the equilibrium constant is given by this expression where delta G double decker equals to negative RT ln K, which is the equilibrium constant for the activated complex. And we can rearrange it to become the equations where K activated complex equals to exponent minus delta G over RT. Taking our previous rate constant expression K2 equals to the transmission coefficients, multiply the thermal energy divided by the Planck constant, multiply the equilibrium constant for the activated complex. Now we can replace or substitute this K double decker with the Gibbs free energy using the expressions that you have seen in the previous slide, which K double decker equals to exponent minus delta G over RT. Furthermore, since the Gibbs free energy change is related to the enthalpy and the entropy by definitions, where delta G equals to delta H minus T delta S, so it is also possible to obtain the rate constant in terms of the change in enthalpy and entropy for the transition state. Now, how do delta H activated complex and delta S activated complex in the Eyring equations can be related to the Arrhenius parameter, pre-exponential factor A, and the activation's energy? We know that the Arrhenius equations, the rate constant is equals to A exponent minus EA over RT, which in the logarithm form, it can be written as ln K equals to ln A minus EA over RT. If we assume the activation's energy is independent of temperature, and then we differentiate the natural logarithm of the Arrhenius equations with respect to t. Okay, so it will be transformed into this expression. Now let's look at the logarithmic form of Eyring equation. We have the Eyring equations here. If we take the natural log, it can be transformed into this form. Okay. We continue the derivation by replacing the ln K for the activated complex with its Gibbs free energy equivalent. Then we get this expression. After that, we relate it with the enthalpy and also the entropy. Okay. So to proceed, we must assume that delta H and delta S are independent of temperature. Next, differentiating ln K2 with respect to T, we get these expressions. Now, we compare the equations that we get from the Arrhenius equations with the Eyring equations. And we equate the Arrhenius differential with the Eyring differential. Okay, so this is what we get by multiplying the RT square it used the core relationship whereby EA can be approximate to RT plus delta enthalpy for the activated complex. Just now we made the simplifying assumption that delta H for the activated complex and the delta S for the activated complex, they are independent on the temperature. Why is this generally acceptable? This assumption holds because the molar heat capacity at constant pressure of the transition state is often very close to the heat capacity of the reactant. If the heat capacities are similar, then the change in heat capacity of activations is very small. So the temperature dependence of delta H for the activated complex is given by these expressions here. If Cp is small, then these expressions will be small. So the delta H for the activated complex will be about the same to the delta H for the reactant. The same logic goes to the delta S. Okay, so the value of the heat capacity for the activated complex is typically quite small, which is in the range of 0.01 to 10 joule per mole per Kelvin. The relationship of the activation energy approximate to RT plus delta enthalpy of the activated complex seems to create a contradiction. We assume that delta H was temperature independent, yet the difference between the activation energy and the delta H for the activated complex that depends on the temperature. This approximation arises due to two main reasons. Number one is the Arrhenius equation is inexact. Second is that although the delta H for the activated complex and the delta S for the activated complex are slightly dependent on temperature, this dependence was completely ignored in the derivations as noted in the previous slide. However, the approximation is usually accurate because the term RT is much smaller than the activation energy or the delta H for the activated complex. For example, at room temperature, okay, so RT is about 2.5 kilojoule per mole, while the activation energy and the enthalpy of activation for most reactions are typically in the order of 10 of kilojoule per mole. This means the approximation of activation energy to the delta H for the activated complex is quite accurate, especially at low temperature. For a more exact treatment, we use the connection of a Van Hoff equation. By relating the temperature derivative of the ln K for the activated complex to the change in the internal energy delta U via this equation. A regular treatment for ideal gas molecules yield the relationship as you can see here. So just now we have obtained this expression, and in this expression, if we substitute the derivative of ln k with respect to dt with this delta u over RT square, okay, then we will get the expressions which is EA equals to RT plus delta H for the activated complex minus delta N for the activated complex multiply RT. This is gain after we substitute the delta U in the equation here. Okay, so the delta N for the activated complex is the change in the number of moles of the gas species upon forming the transition state. Let's apply this to the unimolecular reaction from A to produce the activated complex X. The final state for the activated complex has the number of mole which is equals to 1. And if the initial number of mole is also equals to 1 for the A, then the change in the moles is given as delta N, which is equals to 0 in this case. So if delta N equals to 0, meaning that the delta H for a unimolecular reactions can be approximate to the activation energy minus RT. This is same as the one that we have seen just now in the previous slide. To summarize the thermodynamic form of Eyring equation, we substitute the breakdown of delta G for the activated complex into the rate equation. Okay, so delta G equals to delta H minus T delta S, and we can substitute it into the delta G in the rate of the equation, which results in this piece of expression. Okay, so this equation developed by Henry Eyring in 1935, which is based on the transition state theory and describes the relationships between the reaction rate and the temperature. We have to take note that the transitions coefficient kappa is always assumed to be 1, but is sometimes mathematically absorbed into the entropy term. This form is conceptually similar to the Arrhenius equation, which is also describes the temperature dependence of the reaction rates. The relationship between the activation energy and the delta H for the activated complex differs depending on the reaction molecularity, and this affects the resulting Arrhenius pre-exponential factor when we express the Eyring equation in terms of the activation energy. For the unimolecular gas phase reaction, as we have derived, okay, delta N for the activated complex equals to 0. Therefore, the delta H for the activated complex is equals to activation energy minus RT. Substituting this into the equations of the rate constant, then we will get this piece of expressions. Okay, so we substitute the delta H with EA minus RT. Then we have to do some mathematics to solve it. And eventually we will get the expressions as E multiply the KT over H exponent delta S over R, which is this piece is same as this part here, just that exponent minus EA over RT divided by RT. Okay, needs to be simplified, where minus RT over RT will give us the exponent only, and the other part, which is exponent minus EA over RT, remain here. So this is the rate constant for the unimolecular gas phase reaction. If we have the bimolecular gas phase reaction, which for example involve reactant A and B, okay, then they form the activated complex X. In this case, we will have the NF, which is the final mole for the activated complex, equals to 1, whereas the initial number of mole for the reactant is 2. So the delta N, the number of mole change in the formations of the activated complex, is equals to -1. Okay, so if we substitute this -1 into the equations where we have the EA equals to delta H plus 1 minus delta N multiply RT, we will get delta H equals to, we will get the equations whereby EA equals to delta H plus 2 RT. If we substitute this, okay, delta H equals to EA minus 2 RT into the rate of the reactions, then the final equations for the bimolecular gas phase reactions is this piece of expressions. So you will see that for bimolecular reactions, the rate constant will be different from the unimolecular type of the reactions. By comparing the bimolecular rate constant derived from transition state theory with the Arrhenius equation, we can explicitly identify the theoretical expression for the Arrhenius pre-exponential factor A, whereby for a bimolecular gas phase reactions, this piece of expressions here is equivalent to the pre-exponential factor A, which is found in the Arrhenius equation. So this relationship shows that the pre-exponential factor A, which Arrhenius treated simply as a constant related to the collision frequency, is physically related to the entropy change required to form the transition state complex. Let's work through an example connecting the Arrhenius parameter to the transition states theory parameter for the gas phase reaction between the hydrogen and bromine. Okay, so in this example, we have to find out what is the value of delta H for the activated complex and also the delta S for the activated complex at 1000 Kelvin. Assume that these are the ideal gas, and it was given the value of the activation energy 15.5 kilojoule per mole, as well as the pre-exponential factors is 1.09 times 10 to the power of 11 liter per mole second. The questions involve a bimolecular gas reaction, so we use the relation of delta H equals to EA minus 2RT in order to determine the value of the enthalpy change for the activated complex. So we are given the value of activation's energy and also the temperature. We can substitute both of the value into the expressions and we will be able to find out the correct answer. Throughout the way of these solutions obtaining, we have to make sure that the units are consistent. So we can convert the activation energy to joule per mole or the RT to kilojoule per. Just as the activation energy and the Lorentz pre-exponential factor can be determined graphically from an Arrhenius plot, the change of the enthalpy and also the entropy for the transition state can be determined graphically from a linear rearrangement of the Eyring equations. Starting from the thermodynamic linear form of Eyring equation, as given here, we rearrange this into a linear relationship involving ln k2 over t. So by having this, we can plot ln kt over t versus 1 over t using experimental kinetic data gathered at various temperatures. We obtain a straight line. And the feature of this plot allows us to determine the transition state parameters, where the slope is the negative of the enthalpy of activation divided by R, and the y-intercept provides the entropy of activation. While the Eyring equation is powerful and is considered more reliable than either the Arrhenius equation or the equation derived from collision theory, transition state theory is not perfect and it has limitations. One major limitation is due to the concept of quantum mechanics. Transition state theory treats the transition state as a classical energy barrier that must be overcome. But the quantum mechanics implies that tunneling can occur, where tunneling allows particles, especially the light particles like hydrogen atoms, to bypass the energy barrier created by the transition state entirely. So this quantum effect is especially noticeable when there are low activation energy, because the probability of tunneling will dramatically increase when the barrier height is lowered. Since transition state theory does not inherently account for tunneling, it can underestimate the rate constant in these cases. Another fundamental limitation of transition state theory relates to its primary assumption, whereby an equilibrium exists between the reactant and the transition state phase. In gaseous reaction, this assumption generally holds true, but in reaction occurring in solution, non-equilibrium situations can arise, particularly if solvent molecules do not relax fast enough around the forming complex, thereby upsetting the theoretical framework. So to address these shortcomings, several more complex theories have been introduced. However, the transition state theory still remains largely useful. Its major enduring utility lies in its ability to directly calculate the thermodynamic properties such as the Gibbs free energy change, the enthalpy change, and also the entropy change for the transition state from these overall reaction rates. So it provides the critical physical insights into the mechanism. Before concluding, let's briefly review how the Arrhenius parameter, activation energy, and the pre-exponential are determined experimentally, as we will use this method for comparison in our final example. The Arrhenius equation is given by K equals to A exponent minus activation energy divided by the RT. So we take the natural logarithm to obtain a linear equation ln K equals to ln A minus EA over RT. So the Arrhenius plot graph ln K versus 1 over T. The gradient or the slope of this plot will give us the minus EA over R, whereby the intercept will use the ln A. We treat the pre-exponential factor A as a constant with respect to temperature in this traditional empirical approach. Let's try to solve these questions. Determine the activation energy and the enthalpy of activation for the elementary reactions of A to give us the product of P with the rate constant 0.02 per second at 400 Kelvin and 2 per second at 500 Kelvin. In this example, it highlights the numerical relationship between the activation energy and the enthalpy of activation for an elementary unimolecular reactions of A to P. So we are given two rate constants at different temperature, K1 and K2, at 400 Kelvin and 500 Kelvin respectively. We need to determine the change of the enthalpy for the activation space or the activation complex. So to determine that, we use the linear form of Eyring equation. The slope of the ln K over T versus 1 over T. Okay, so we use this equation where we plot the graph of ln K over T versus 1 over T, and we will get the slope from this line, okay, as delta H over R. So the slope of the plot ln K over T versus 1 over T is negative delta H over R. To find out the slope, we find out the difference between the y coordinate versus the x coordinate. Therefore, we have ln coordinate for the y, which is 2 over 500 Kelvin, okay, K over T minus ln coordinate y2, which is 0.02 over 400. It is something similar to a plot, okay, when you plot the graph. So you have the graph of ln K over 2 as the y-axis and 1 over T as the x-axis. Then you will get a straight line, a linear plot. So you get the coordinate of this point and this point for the temperature of 500 Kelvin and 400 Kelvin. Okay, so you get the slope with y coordinate. You find out the difference divided by the difference of x coordinate. Okay, then you will get the value of the slope. So from the value of the slope, you multiply with the gas constant. Then you will be able to find out what is the value for the enthalpy change. To determine the Arrhenius activation energy, EA, using the kinetic data provided, we start with the linear form of Arrhenius equation, ln K equals to ln A minus EA over R T. Just like what we did for delta H activation on the previous slide, we find EA from the slope of a plot of ln K versus 1 over T. The slope is equal to negative EA over R. Using the rate constant we were given, okay, so the rate constant K equals to 0.02 per second and at the 400 Kelvin, and K equals to 2 per second at 500 Kelvin, we can calculate the slope, where this is the y coordinate difference and this is the x coordinate difference. Solving for the activation's energy EA, it is equals to the value we obtained from this part here, multiply the gas constant. Now we can compare this Arrhenius activation energy to the enthalpy of activation delta H. We calculate previously on the slide just now, whereby the delta H equals to 72.9 kilojoule per mole. And the difference between the EA and delta H is 3.7 kilojoule per mole. This difference confirms the derived theoretical relationship for this type of reaction, which is the unimolecular reaction based on the earlier derivations with EA approximate to RT plus delta H. If we take R, multiply the average temperature, which is between the 400 and also the 500 Kelvin, equals to 450 Kelvin. When 450 Kelvin multiply R, the value is approximately 3.7 kilojoule per mole, which exactly match the calculated difference of this one. And this confirms the derived link between the Arrhenius parameters and the thermodynamic parameters of the transition state theory.